Okay. So, this is the gadget that we had, right, and what we argued. So, these are the 3 external edges. So, what we want is for every proper subset of the external edges, okay, there should be a unique cycle cover, that is what we want. So, what we saw last time is that this gadget has the property that for every proper subset of the external edges, there exists a cycle cover, and if you take all the 3 external edges, then of course, you will not get a cycle cover because this vertex will remain uncovered. So, that we saw last time. So, the question was, can we, so clearly, so this gadget is not correct in the sense that it does not give us what we want. That will not harm. You can have multiple edges in the same direction, and later on you can replace it with one edge having. So, one way to mend that is what you can do, you can introduce an intermediate vertex here and here. Okay, so, suppose you have something like this, okay, you can replace it with a graph which looks like this. Okay, and let us say that this edge had a weight w. You give these 2 edges, let us say the first edge you give 1 and the second edge you give w. So, the product still will be w, but now you have taken care of multiple edges. So, getting rid of multiple edges is not a big deal, or parallel edges, that is easy. But the question is more basic. What we want is the clause gadget to have the property that for every proper subset of the 3 external edges, there should be a unique cycle cover, and that is clearly not the case, because suppose I take only this external edge, I will have 2 cycle covers. So, one is I take this, then this and this. So, this is one cycle cover, and I can also take this, I go up and then come down. Yes.
Cycle cover, can cycle cover be, I mean, like consist of 2 disjoint cycles?
Yes, yes. It can consist of any number of cycles, but they should be vertex disjoint.
So, the weight would be, I mean, the
product of the weight of the edges, weight of one cycle cover. No, I think only 2. So, if I only have this external edge,
yeah, you can go for this and return to the same vertex again.
No. So, vertices cannot be repeated in a cycle cover.
I am not repeating it.
Okay, so you come here and then
go back using the vertex.
Okay, but then this vertex.
We have covered one in everything.
Okay, and then you take these 2. Yes, that is true. So, you have more than 2 actually. So, how do you, so any idea how this can be fixed? So, let me give the solution. So, again the solution is just to remove these 2 edges. So, what we will have is, I mean, so this is just one solution that I came up with, but I am sure there will be other solutions as well. Okay. So, these are the 3 external edges, and basically I have removed these two pair of edges. So, this pair and this pair. So, I think this works. Okay, so this is not the correct one. So, this so let us just check, I mean maybe that is the best way. So, suppose if we have none of the three external edges, then our cycle cover will be basically taking these two and these two, right. Suppose if we have this edge, then we can go this way. Yes.
Suppose if we have only one outlet that is an overall,
Uh-huh.
then sir, as sir listed, I can do one cycle to cover the lower vertices.
Yes.
Vertices and one cycle to cover both the upper vertices.
Yes.
And then sir, one cycle can also be separate. From this to this, and then that again, and then I will go traverse up and then back down.
Okay, maybe I will just remove this edge. Does that help? That does not help, right. So, what construction did I have? Yeah, that is true, right. If I have only this, then so suppose if we remove this edge,
So then we have no vertex cover in case of we don't use any external.
yeah. Okay, I will check this. I am sure that this something similar will work, but again I am not able to get the correct solution at this point. But basically some subset of this graph actually works. Okay. So, I did have a construction earlier. So, what about the other cases? So, suppose if we have only this edge, then we have a unique cover, right. All the cycle covers here will have weight 1 because all the edges have weight 1.
Can we change some of the weights so that
No, I think it will matter. I mean, at least even if you look at the book's proof, what they actually want is they want a unique cycle cover for every proper subset. But anyway, so I'll try to fix that. But clearly, what is there in the book is not correct. Okay, but I am sure it is fixable. So let us just make that assumption for the time being, and let us see what we how to argue the proof. So now suppose we have okay, so let us look at a small example to illustrate the idea. So let us say that our Boolean formula phi is a formula which looks like this: x1 or x2 bar or x3 and maybe x1 bar or x3 bar or x4. Okay. So, the corresponding graph that we will have is, firstly we will have a variable gadget for each of the 4 variables. So, this is for x1, x2, x3 and x4, and we will have a clause gadget for the 2 clauses. So, now since x1 appears once as true and once as negated form, we will have a true edge and a false edge. For x2 we will have just one false edge. For x3 again we will have one true edge and one false edge, and for x4 just one true edge. Okay. And now we need to connect them to the clause gadgets. So, all the clause gadgets have 3 external edges. So, C1 gets connected to the true edge of x1, and this happens using a XOR gadget. To the false external edge of x2 and to the true external edge of x3. Okay. So, similarly for C2 as well. Okay. So, this is the entire connection. So, even for arbitrary number of variables and clauses, you can see that this can be constructed. So, now why how do we get the number of cycle covers here? So, that needs to be argued. Okay. So, before we argue that, how many XOR gadgets do we need? So, if we have n variables and m clauses, how many XOR gadgets do we need? 3n. Okay. So, what did we argue earlier? Yeah. So, what we said yesterday was that there is a 1-to-1 correspondence between assignment of values to x1 up to xn and cycle covers of these gadgets, of the variable gadgets. Okay, because for each variable gadgets there are exactly 2 cycle covers. Also, the other thing that we claim is that for every proper subset of the external edges of a clause gadget, there exists a unique cycle cover in the clause gadget. And both these cycle covers are basically cycle covers of weight 1, because all the edges in the clause gadget as well as the the variable gadgets have weight 1. So, any cycle cover also has weight 1. It is only the XOR gadgets which introduce larger weights or negative weight cycle covers. Yeah, so this again as I said we will verify later on, but let us just assume that the second claim is true. So, now let x bar be an assignment to the variables of the formula, and for this assignment let C x bar be the set of cycle covers in G. So, I use the name G for the graph, is it? So, can you just check for the entire graph that we construct from phi? G, right? Okay. So, yeah, so for every, so once we fix an assignment to the variables, let C x bar be the set of corresponding cycle covers, and let W x bar be the sum of the weights of cycle covers in Cx. Okay. So, the final claim is this, that if phi of x bar evaluates to true, then W x bar is 4 to the power 3 m, and if this evaluates to false, then is 0. So, this is where we left yesterday. Each XOR basically multiplies the weight into 4. Whatever is the weight in the original graph, if you put an XOR gadget and replace its two end edges, it basically multiplies the total weight into 4. Okay, so that is what that is what is the property of this edge. So, yeah, so that is not quite true. So, the thing is that if exactly one of these two edges are included in the cycle cover, then it gets multiplied into 4, otherwise it is 0. Okay, so, that is what we said yesterday. So, why is this claim true? So, let us look at a satisfying assignment. So, let us look at an x bar which evaluates to true. So, then what property does each clause gadget have? So, suppose I consider an x bar, and in the cycle covers I consider the cycle cover for each variable as being the cycle cover taking the true external edges if that variable is set to 1, and I consider the cycle cover in the variable gadget as taking the false external edges if that variable is set to 0. Okay. So, for example, in this x bar, so suppose x1 is set to 1. So, then I will consider this particular cycle cover. Okay. So, we saw that there are exactly two of them, we will consider the top one, and if x1 is set to 0, we will consider the bottom one, and we will do this for all variables. So, what can we say about the clause gadgets?
No clause has empty external edges set.
Right. So, what we want finally is we want to have the total weight as 4 to the power 3m. So, basically what we want is that all the XOR gadgets should have the property that one of its end edges is true and the other end edge is false. Okay. So, that is what we want. So, suppose in this clause, what are the 3 literals? The 3 literals are x1, x2 bar and x3. So, suppose x1 and x3 are true, okay. So, then we will consider the cycle cover in C1 which does not include x1 and x3. I mean the external edges corresponding to x1 and x3. So, we will only consider the cycle cover in C1 which has this external edge. So, this is where we crucially use the fact that there is exactly one cycle cover corresponding to every subset.
But so all 3 literals are.
If all 3 literals are true, we will consider the cycle cover when none of the external edges are present. Okay. So, there is again one cycle cover when none of the things. So, basically it gets negated. So, if you have a literal as being true, the external edge corresponding to that literal gets omitted from the cycle cover.
So basically, what we are there will be the cycle cover present, but the actual contribution it will be 0 in the sum of the.
No, I am not saying that. So, what I am saying is there will be a unique cycle cover which will have the property that for every true literal, the external edge corresponding to that literal is not present in that cycle cover, is not present. Okay. So, in other words, if there is for example, a clause which is completely false, that is all its 3 literals are true, all the 3 external edges must be present, but we know that there is no cycle cover which has all the 3 external edges being present. Okay. So, now what we have, so that is how we set the cycle cover for the all the clauses. So, we look at the variables, we do this setting, and now since it passes through 3m XOR gadgets, the total weight of these cycle covers will be 4 times 4 times 4 times all the way how many ever XOR gadgets you have. Okay. So, the total weight will be 4 to the power 3m. And suppose if you take a assignment where which evaluates to 0, then you will run into problem, because then there will be some clause in which all its literals are false. So, now if you try to set that clause, I mean if you try to consider a cycle cover for that clause, you will have to omit at least one external edge, but if you omit one external edge, in the variable corresponding I mean in the corresponding variable, that edge is also omitted, right, because that clause, I mean that literal is set to false here. So, both these things are omitted, and by the property of the clause gadget, if both its end edges are omitted, then its total weight contribution is 0. So, that weight assignment will contribute to 0. Okay. So, that is basically then. So, the basic idea is that I mean forget about the XOR gadgets for the time being. You have these individual components, I mean your entire graph consists of these m components corresponding to the clauses and n components corresponding to the variables, and you want to have the property that if a literal is set to a certain value, you take a certain cycle cover in the variable gadgets, and if a clause gets set to true, I mean if whatever are the values that gets set to true in a clause gadget, you take the corresponding cycle cover in the clause gadget. And now you want to multiply all these cycle covers and that happens using the XOR gadgets. Okay. So, yeah, so the basic thing is that it is not something very intricate happening here, but the clever part of this whole thing is this construction. So, once you have the construction, then the rest of the analysis is not difficult. Okay. So, any questions? Yeah. What? Yes. When I am omitting an external edge, see, when do I omit an external edge? So, I omit an external edge if that literal is getting set to true in my assignment. Okay. So, if that literal is getting set to true in the assignment, which cycle cover do I take corresponding to that literal? So, if that is a positive form literal, I take the cycle cover corresponding to the true edges, okay, which means that that external edge gets included. And if that is a literal in the negated form, for example, if that is something like x2 bar, then I take the cycle cover corresponding to the false edges. Okay. So, in other words, the external edge that is being taken, right. Each XOR gadget, each XOR gadget does not contribute 4. Whatever is the weight of the original cycle cover, replacing these two edges with whatever that thing was, multiplied the weight 4 times. So, if the original weight was W, the weight of the new cycle cover, the sum of the weights of the new cycle covers is 4W. Okay. It is not that you get only one cycle cover by replacing these two edges. You get a collection of cycle covers and the total sum is 4W. Okay. So, that is also something that you should verify. I left that as an exercise yesterday, but if you have not verified that, please go back and look at that construction. Okay. So, if you look at the total sum of all those things, that will be 4W. So, what property do we have now? So, what we have here is that, so suppose this x1 literal gets set to true in x bar. So, then this edge is included in the cycle cover, but in the cycle cover for C1 this edge is not included, which means that now the clause gadget has the property that one of its end gadgets is included. So, whatever weight was there in the original graph, that gets multiplied time into 4. So, let us say if you start without any clause gadgets, so you have a unique cycle cover for the entire graph. Okay. So, for the first clause gadget, so that gets multiplied into 4. So, you have so the total weight is 4 for this XOR gadget. Now, for the second XOR gadget, again that gets multiplied 4 times. So, that is 4 square, and then finally it will be 4 to the power 6. So, these XOR gadgets are only ensuring that both these things should not appear simultaneously, that is all. Yes. Cx bar will not be empty, Cx bar will contain lots of cycle covers, but their total sum will be 0. So, Cx bar can contain cycle covers, but it is only that their sum will be 0. So, I will give you a very simple cycle cover, well no, I cannot just construct one, but maybe you can look at a even more simpler formula and just try it out. Try looking at a formula and try looking at a non-satisfying assignment, and you will see that you can construct cycle covers basically based on these XOR gadgets, but there will be 2 of them that will cancel each other off. suppose clause 1 is not satisfying. Yeah, so suppose this has a value 0, 1 and 0, right. No, so then what happens? So here I will be taking this cycle cover, right. Here I will be taking this cycle cover, and here I will be taking again this cycle cover. So now for yeah, exactly. So now for this clause to contribute something, what should happen is that all these 3 external edges must be present, because here this external edge has got omitted. I mean, I am sorry, so this external edge, no. So this external edge is omitted, here this is omitted, and here this is omitted. So here all 3 of them must be present for this to make any sense, but that we know is not. Not only the middle one, all 3 of them. Okay, yeah, the middle vertex in that clause, yes, that will not get covered. There is no cycle corresponding to C1, but then C1 is part of your entire graph. So if you have a cycle cover for the entire graph, that better cover that middle vertex for C1 as well.
Where is the sum of the weights going to 0?
No, but here I am not getting a cycle cover. The weights will go to 0. For example, if let us say I include this edge, okay, or I am sorry, let us say if I exclude this edge. So if I exclude one of the external edges, then I know that in C1 there is a cycle cover, right. Basically the cycle cover which includes this and this. But if this edge is excluded, this XOR gadget has the property that if both its end edges are excluded, then the total sum of the cycle covers that is present inside that XOR gadget will sum up to 0. So that is why I said that you actually need to explicitly construct a formula together with the XOR gadget to find out which 2 will cancel each other off. Okay, so it basically comes from this XOR gadget.
So why are you not taking all the external edges of C1?
Because that cannot be done. That is the property which C1 has. Because ultimately that is what I want, that if a clause is unsatisfiable by a certain weight assignment, somehow I should not consider that assignment in my final count. That is what I want. Okay, so I will leave it at this point. So again what I advise is you go back and check this yourself, okay, verify some of the gadgets and convince yourself why this is correct. Okay, so what I will do next is we will start upon what is known as interactive proofs. So I think this is chapter 7 in your textbook. 8, okay. Yeah, so we'll just leave the permanent function for the time being, but later on again we'll come back to this permanent function. Okay, so what is an interactive proof and what significance does it have with respect to complexity? So this notion of interactive proof again is something very natural. Okay, so I'll explain it in a minute. So the model that that we consider is the one consisting of let us say 2 persons. So there is a prover and there is a verifier. Okay. Okay. So basically, so what I want to look at is I want to look at a computational model. Okay, basically a model which accepts certain languages, where given an instance, so suppose you are given some x, there are 2 persons sitting over here. So there is a prover and there is a verifier that have the following properties. So the prover is all powerful. So this So, this guy has all computational resources available to him. I mean, you can also assume that this guy can decide undecidable languages. Okay, so there is no restriction on the power of the prover, but the verifier has certain restrictions. So later fix this. So bounded amount of resources are available, and what are their goals? I mean, the goal of the prover is to somehow convince the verifier that X belongs to the language. So his goal is to convince V that X belongs to the language, but this guy, this verifier guy is skeptical in nature, so he won't accept an X until and unless he is satisfied that whatever the prover is telling him is a correct proof of the fact that X belongs to the language. So his goal is to, so how do I state this? And convince himself okay. So in other words, what you can think is that, I mean, his goal is to somehow reject the fact that X belongs to the language. Okay. And again, when we assume that such a model exists, we will always assume that these are fair people. I mean, they cannot cheat one another. Okay. So yeah, so this is basically the general model, and what we will look at is, we will look at various types of verifiers with various kinds of restrictions upon them. For example, what if the verifier is someone who can only perform deterministic polynomial time computations? Okay. What if he is allowed access to random bits? Okay. How does the model change? Okay. Verifier can be NP also, yeah. That will lead to a more powerful class of languages. Yes. So bounded means that there is some bound on the computational power of the verifier. Okay.
Suppose verifier is NP.
Yes.
Prover has to provide the certificate.
No, so don't. So don't think of the certificate model for the time being. Okay. So don't think about that. So the way to think of this is that, so there is this guy verifier who asks questions to the prover given an input X, and then based on the responses that the prover gives, either the verifier will ask more number of questions, or finally he will decide whether or not to accept X. Okay. So there is basically a dialogue that is going on between these two persons. Okay. If verifier is NP, then I mean, what do you mean by does it matter?
The resultant language will be in NP or not?
Of course, the resultant language, yeah, I mean, the complexity of this entire model cannot be less than the complexity of the verifier. Okay, because say, let's say the verifier is in some complexity class C, given an input x, I can always just take that input and run that machine for the verifier and accept or reject based on that without even asking the prover what to do.
I'm saying that let's a language have NP certificate.
You mean to say there is a language in NP?
There is a language L which has a certificate which can be verified.
What do you mean certificate for a language?
There is a machine.
So basically you have an NP machine for L. Okay.
I'm saying that in the definition of NP, the verifier was polynomial line. If we give it NP, the power of NP, then what will be power of the result? Can it go outside NP?
In the definition of NP, I don't think so. I don't think so, because what would that mean? So that would mean that there exists some certificate which makes the verifier accept that string. So if the verifier is also in NP, it means that there exists another certificate, okay, which will put that in the language by means of another polynomial time verifier, but now you can just concatenate those two certificates. So that will be still in NP.
So suppose a verifier is a point and prover gives a certificate so as to decide say sigma 2p NP. So it may act as a kind of certificate which when augmented with a 1.
So you mean in this model or in that?
No, suppose when say verifier is an NP language, then verifier itself can verify and
It can,
the NP language
right.
without using prover.
Right.
So if at all let's say verifier is a ONP machine,
Okay.
you wish to decide sigma 2p NP.
That is not clear why it can decide sigma 2p.
No, but then sigma 2p is like ONP with a certificate. I mean the real is part of sigma.
Yes.
So prover is something like which gives a certificate to the verifier.
So not exactly. So there you have the thing that for all certificate, I mean there exists some certificate, let's say C1, such that for all possible certificate C2, there is a polynomial time machine which accepts given this C1 and C2 along with X. But here that is not the case. Here you do not have access to, I mean you cannot claim something like for all possible certificates. Here basically,
I am saying prover is already in C1 and since verifier is an ONP machine, so for all C2 that can be done by verifier. So prover is providing C1 to verifier.
so basically here, I mean, so let me define the model precisely. So this was just an informal notion, but here, I mean, as we shall see, so this model does have a lower computational power than this there exists for all alternation, okay, because here what is happening is basically a set of question answers. So this guy asks a question and he gets just one answer for that question, okay. So a question and an answer is basically just one string. So he provides some string to the prover and the prover takes that string and based on what that string is provides another string back to the verifier, and this dialogue continues for a certain number of steps and then the verifier accepts, okay. So the number of strings that can be interchanged is bounded by polynomial by the definition of this model. So
kind of seems counterintuitive that verifier has been given bounded among the associated.
no, it is not counterintuitive. So let me give you an example. So suppose you are the prover, okay. So suppose the prover in this case is the student, okay, and the verifier is myself. whatever. So now the goal of the teacher, so basically I give you a question and your job is to convince me that whatever solution you are providing me is correct. Okay. So you can use whatever knowledge you have, you can look up any book, anywhere, anything, but then I will be only convinced if there is a step by step deduction in whatever proof you give me. Okay. So I will basically go through each and line of your proof, and if the current line follows from the previous line, only then I will be convinced that the final answer that you have is correct. Okay. So the goal of the prover is to convince that whatever is the input that belongs to the language, but the verifier can only have a certain amount of resource, and within that he has to check whatever the proof the prover is giving is correct or not. Okay. So yeah, so this is one example that you can, yeah.
Prover cannot give any statement until and unless verifier asks him to.
And the prover can give a statement, can give a statement.
But then what does it
But in that case,
But how
verifier will
does-
just discard it.
Huh?
The verifier doesn't.
Yeah, I mean if you give a statement which doesn't make sense, the verifier will discard it, and if it makes sense, then I mean well and good.
The number of questions will be polynomial.
Number of questions is polynomial.
Depending on the condition.
Yeah. So let me define the formal model here. This is interaction of. So we will define a general model first, and then we will look upon restrictions on the verifier. Interaction of deterministic functions. Okay, so this stands for deterministic. So suppose you have two functions f and g from 0 1 star to 0 1 star, and you have some number k in which is a positive integer. So given an x, so given a string x, k round interaction of f and g is a sequence of strings a1 through ak such that a1 is the answer of f of x. Okay. So then so basically a1 is something which the verifier initially computes given x, and then he sends a1 to the prover. So a2 is what the prover computes given x and a1, and then he sends his answer back to the verifier. So a3 is f of x comma a1 comma a2 and so on. So finally a 2i plus 1 is f of x comma a1 up to 2i So, of course, whatever answers are being provided in a certain round of interaction are known to all future rounds. So, both the prover and the verifier has access to all the answers in the previous rounds. Yeah, so a k round interaction is a sequence of strings A1 through AK such that these strings have this property, and the output of, so what is this called? So the output of end f at the end is denoted as out f comma g on x, and this is basically whatever is f of x a1 up to ak. So finally, when the k rounds terminate, whatever is the value of f on all the answers that he gets is basically the output, and this we will assume is some binary number. So this is basically whether x gets accepted or rejected. Huh?
A1 to AK is the value.
No, these are strings because these are the answers, but whatever is the final output, because ultimately I am given an x. Okay. So at the end of my question answer session, I have to finally output whether x belongs to the language or it does not belong. Okay. So finally I will just output 0 1. Huh? Yeah, so it does not matter actually. I mean, if k is odd, you can just add one more dummy step. So basically, if k is odd, it means that the last question is being asked by the verifier and its answer is not being used. So it is basically the same as not asking that question at all. Okay, so we can assume that k is even. Yeah, so in this model what we were assuming is that f is our verifier and g is the prover. So this is the general model. So now let us look at complexity bounds on these functions. So we say that a language L has a k round deterministic interactive proof system, deterministic interactive proof system if there exists a deterministic polytime function v such that for all strings x, if x belongs to L, then there exists a function p So basically it means that there exists some prover such that output of the verifier on x is one, and if x does not belong to L, then for all provers, okay, I mean for all functions from strings to strings, the output is zero. So, basically no prover can ever convince the verifier.
There is no
Verifier
polynomial
would be same.
in the definition.
Huh?
K around deterministic interactive system. There is no polynomial in the definition.
Yeah, so okay, yeah, so maybe we can make this more general, but then yeah, one second. Yeah, K should be polynomial here.
This last occurrence does it belong to and then for all the provers and for all the verifiers we have why we are changing for all the provers? If we assume that all the provers have same power.
One second. Yeah, so for all x, there is a K round interaction with any function p, with any p such that this happens. Okay. Yeah, so what were you asking?
Why we need to take all the provers? We assume that all the provers are of the same power.
All the provers are of same power. I mean, you can assume that.
Unique for all provers.
No, this means that no matter what function you consider, so prover is basically a function. Okay, given some string, it outputs some other string. So, no matter what function you consider, okay. So, when we say that the prover has unlimited power, what we just mean is that to compute that function, we do not assume any restriction on our computational model. Okay, it can be an all powerful model. Okay, but what we mean here is that no matter what function we consider, that can never convince us that x belongs to the language. I mean, that is what we want. Okay, so for example, if you look at an NP language, let us say SAT. Okay, so if I want to convince ourselves that a Boolean formula is satisfiable, what we want is basically one satisfying assignment. Okay, there should be somebody who provides us a satisfying assignment. But if I want to convince myself that a formula is not satisfiable, no matter what formula, I mean no matter what function I consider here, I will never be able to get a, I mean I should never be able to get a satisfying assignment. Okay. So, it is very important that this should work for all possible functions. Yeah, so here, yeah, so since I did not have any polynomial time constraint here, we can look at just a general definition, but then we can define the class DIP. So, DIP is the class of all languages where V is a polytime computable function. Okay. So, what is this class DIP? I mean, how what is the complexity? Certainly NP is contained in this class, because if we have I mean if we consider a language in NP, I mean I can always choose our prover to be the one who provides this certificate. I mean if you look at the certificate based definition, given an instance, the prover is one who just provides the certificate, and then the verifier just plugs it into its polynomial function and does it. But what about the other side? I mean how, so is it any more powerful than NP? Yeah, so I am running little bit over time. So, can I take 15 more minutes? Is it okay with everybody? Okay, so, I just want to complete this part. Yeah, so basically what we said is that so this is trivial, but what about so k is polynomial in the length of the input. Yeah, so no, I think we can also say that k is bounded by polynomials. So, yeah, we can say it here, I guess. So, there is a class of all languages V, where V is a polytime computable function, and let us say k is some polynomial in the size of x. So, the number of interaction is not more than polynomial. So, yeah, so as it turns out that these two classes are actually the same. So, and the proof is not very difficult. So, how do we prove it? So, let us pick a language in DIP. We need to give it a an NP definition. So, that is we need to give a construction of a certificate. So, what should the certificate be? Right. So, the certificate will be just a concatenation of all the answers that the verifier gets, together with the questions as well, but the questions does not really matter. And so, what does the what is the polynomial time? So, yeah, so we have the verifier, but so what does the verifier do? I mean, verifier just computes these A1, A3 and all these things. Basically, he just computes the questions, right?
Last f of x a1 to ak which linear, so we can actually do that.
So, that is the function v here, but that is not sufficient. Okay. So, it is not just sufficient to look at the last step. So, what the verifier needs to check here is that, okay, yeah, so need to verify that v of x is a1, v of x comma a1 comma a2 is a3, and so on. Okay. So, he needs I am sorry. So, this is not correct. So, x comma a1 is a2. So, he needs to verify the answers of the prover. And so on. So, given a certificate, the verifier basically checks that all the answers are the correct answers or not, depending on the questions that he had asked. So, this is so this is not exactly the same verifier. So, what we are constructing is a polynomial time machine, let us call it V prime, which does all these checks. Yes.
So this computation might be very expensive.
No, the computation of A2 is very powerful, but then he has the answers. Okay. So, the this machine V prime has already been provided with this certificate. Okay. So, in again the proof I mean the prover verifier model, think of the thing that I already have your solution. Okay. So, now I am just checking that corresponding to the questions that I had asked, whether the answers are correct or not. Okay. So, he already has access to this certificate and he does this step by step verification. So, now what if string x is in the language?
So what is the guarantee that that verification is correct in my time?
Huh?
What is the guarantee that that verification is correct in my time?
Because V is a polynomial time machine, no? V is a polynomial time machine. So, tell me now.
X belongs to L, then all of these verifications will be good.
Yeah, exactly. So, if x belongs to L, then there exists such a certificate, which implies that finally whatever is the answer. So, all the steps correctly give whatever are the AIs, and the final answer is yes. And yeah, and what if x does not belong to L?
At least one of these steps.
So, what do we mean by that? So, x does not belong to L means here that for all prover functions, this is 0.
There is no certificate such that all the steps correctly be verified.
Right. So, basically that for every certificate there is at least one step where it will not match with whatever V is computing.
It's not only she can get a certificate that all these steps matches.
Right.
The final answer will be no.
Final answer will be no. Yeah.
Because we have a prover which are
So that
So, the final answer is also a computation of one of these steps, right?
final answer is computation of all, we take all the A1 to AK.
Right.
We get a 0 or 1. It is not a string in that case. Last because we are not considering it is AK.
But I think the way we defined it, we do consider it as a string. So, we do consider it as a string that is being outputted in the last step. So, if you recall, it was f of x A1 through AK, and we assumed that it outputted a binary number. Okay. So, in the last step of this thing, it will output a 0. So, yeah, however way you want to look at it.
In each step it can output a string, but in the last step it will only output a binary 0.
Yeah. So, what is the point behind this? I mean, the point behind this is that since we have restricted our number of rounds to polynomial, it does not matter how many rounds we perform, how many questions we ask, we can always concatenate all these questions. Okay. It is basically that I am concatenating all these questions and then asking the prover something, and then depending on that I am either accepting or rejecting. Okay. There is always a way to go about doing that. So, this is the crucial difference between let us say something like sigma 2, where you have alternating quantifiers and this interactive model. So, yeah, so the point is that this is not very interesting because it does not give any power in addition to NP. So, what does make it interesting is if we make the verifier probabilistic. Okay. So, suppose the verifier is not a deterministic machine, but a probabilistic machine. So, in other words, okay, so let me just define it this way, that given K, L has a interactive proof system if there exists a probabilistic polynomial time function V such that for all x there is a there is a k round intersection, I am sorry, k round interaction with any function p such that if x belongs to the language, then there exists a prover such that the probability that V accepts is greater than 2/3, and if x is not in L, then for all functions p, probability that again this guy accepts is less than 1/3. Okay. And the way the notation that we use to denote this is that we say that L belongs to I p of k. Okay. So, this k basically denotes how many rounds of interaction is required to put L in this class. Okay. So, what is the interactive proof model that the interactive proof model that I am using? How many interactions does it have? And yeah, we say that the class IP is just union over all C of I can just say n to the power C. So, this, as we shall see that this model is more interesting. So, the moment we make the verifier probabilistic, so now basically what the verifier can do is that he can toss coins. Okay. So, I want to check whether some of your answers are correct or not. So, I will just toss some coin and depending on that I will grade you. So, let us just look at some properties of this class, some things that we can assume without loss of generality. So, firstly, this probability can be amplified. Okay. So, same as what we do in BPP, we take multiple trials and then we take the majority of the answers. If we do the same thing here and the same proof technique, basically just apply Chernoff bound to and you will get that it can be amplified. So, that is one thing. There is also a very interesting property that this class exhibits, that is what we can show is that for x in L, we can how do I say this? For x in L, we can amplify the probability all the way up to 1 actually. Okay. So, in other words, we can make this a one-sided error computation. So, this is not something that is very intuitive, okay, because as we saw for the case of RL and RP and BPP, you can only amplify your success probability, but you cannot make it one sided from two sided. Okay. But as it turns out, in the case of IP, this can be done, okay. And this is actually a non-trivial construction. So, we will not prove it right now. So, maybe a few classes later we will look at a proof of this. Okay. So, let me just yes.
Similar to if set belongs to BPP, then RP could be NP.
You are looking at answers of your set, right? Yeah. No, so the proof that we will look at is definitely not similar to that. No, I do not think this will actually give you the proof. So, that is basically using the fact that SAT is self reducible. So, you can compute a satisfying assignment if you have access to SAT, but so we will see later. So, when we will come to this, we will see how the proof goes. So, what other things that I had?
Something similar to ZP.
You mean to say that the verifier is, so the verifier runs in expected polynomial time with no error at all? I do not know. Yes, for BPP and RP, I mean whatever are the corresponding notions here, they are equal, but for ZPP I do not know. For example, yeah, if you have zero sided error here, what it gives, I am not clear. I will try to see that. Okay. So, the third thing is that making the prover probabilistic does not help. Okay. So, anyway, I mean your prover is an all powerful machine. I mean, if you make it probabilistic, what you can do is that you can have another prover who runs through all the coin tosses of this original prover and then just take the majority, because if it is a probabilistic machine, it should accept on more than half the sequence of coin tosses. So, I can just simulate all the sequences and take the majority again. Okay. So, that does not help. And the final property that I will state, again we will look at its proof at a later time, is so without loss of generality, we can assume that this prover So, here P means the prover, okay. So, do not confuse it with the class P. So, this lies in P space. Okay. So, in other words, even if you consider a function which has more computational power than P space, it can actually be simulated by some other function which lies in P space. So, P space, I mean the power of P space is sufficient to capture the complexity of this prover and also preserving this definition. Okay. So, even if you restrict the power to P space, we will get the same set of classes, the same set of languages. So, this again is not very difficult to show, but we will look at an argument maybe later on. Okay. So, yeah, I wanted to do an example also, but I think I will stop here. We are already quite over time.